Inequalities are very much like equations, and I'm not going to spend too much time on inequalities because really all of the techniques you've learned for equations, linear equations, can be applied to linear inequalities. There's one big wrinkle or one big exception though. First, a little bit of terminology if you haven't seen these symbols in a little while, just to make sure you're up to date. The sort of arrow pointing to the right is read as greater than. If there's another bar below it, it's greater than or equal to. A little arrow symbol pointing to the left is less than. A little bar below it means less than or equal to. Now, to demonstrate the difference between equations and inequalities, I've written 4 statements, all identical, and I'm going to show you what happens when I do different things to them. So 5 is greater than 3. This is a true statement. Now, some of the things I can do with equations. Well, I can add the same thing to both sides. Well, what if I add 6 to both sides of this inequality? Is it still a true statement? So the left-hand side becomes 5 plus 6, which is 11. The right-hand side becomes 3 plus 6, which is 9. 11 is still greater than 9, so that's fine. How about subtracting? Well, what if I subtract 4 from both sides? So 5 minus 4 on the left, 3 minus 4 on the right. The left-hand side becomes 1. The right-hand side becomes negative 1. Negative 1 is greater than 1. Or sorry, 1 is greater than negative 1. If you ever get confused, always think to yourself, where are these things on the number line? I'm going to be drawing some number lines in a second. So if you're not sure what a number line looks like, you'll see it in a second. Greater than really just means to the right of on the number line. So 1 is to the right of negative 1 on the number line. So this is a true statement. So far, so good. We can add something to both sides of an inequality without worrying too much about it. We can subtract something from both sides of an inequality. What if we multiply both sides of an inequality by the same thing? Well, if we multiply both sides, let's say by 2, 5 times 2 on the left, 3 times 2 on the right, we get 10 and 6. 10 is greater than 6, so again, no problems. But what if we multiply by a negative? I'm going to multiply by negative 3. So 5 times negative 3 on the left, 3 times negative 3 on the right. This becomes negative 15, and this becomes negative 9. Now remember, greater than means to the right of on the number line. Negative 15 is actually to the left of negative 9, and so negative 15 is less than. As soon as you multiply by a negative, you have to change the direction of the inequality. And that is the one difference between solving inequalities and solving equations. So let's take a look at a couple of examples. 3x plus 5 is greater than 17. The instructions here would be to solve. And just like with equations, what you're trying to do is find all values of x that will make this a true statement. But unlike the linear equations we saw, instead of having just one solution, one number that makes the statement true, we're actually going to have an infinite number of possibilities here. And there's a way to graph this to show that sort of infinite possibility. So just treat this like an equation, with the caveat that if you multiply or divide by a negative, you have to change the direction of the inequality. So here we have 3x plus 5 is greater than 17. Let's isolate the 3x. We'll do that by subtracting 5 from both sides. Subtracting, remember, is no problem. So 3x is on its own. If I subtract 5 from 17, I get 12. So now to isolate the x, I want to divide both sides by the coefficient 3. It's positive, so I do not have to change the direction of the inequality. I can just divide the left-hand side by 3 to get x, and divide the right-hand side by 3 to get 4. So I have x is greater than 4. So what this means is the solution to this inequality is any value of the variable that's greater than 4. And I can demonstrate that on a number line when you want to do this, write the solution on a number line, you just put the 4, which is considered like a boundary value, right in the middle. Put a couple of marks on either side. So there we have the 4. Always increase as you go from left to right. So 4, 5, 6, 7, 3, 2, 1. And then if it's a strict inequality, which means a greater than as opposed to a greater than or equal to, you put a hollow circle around 4. And x is greater than 4 means all values of x that are greater than 4. So 5 is greater than 4, 6 is greater than 4, etc. But not only just those integers, also values like 4.1 or 4.2 or 4.01. In fact, we can get as close to 4 as we like, and it'll still be a true statement. It's just not going to be true if we have 4. If you substitute 4 into the original inequality, you have 3 times 4 plus 12 on the left, which is 17. Well, 17 is not greater than 17, and so I can't include that as part of my solution. But ever so slightly to the right of 4 is part of the solution, and that's why you need the hollow circle to mark the boundary, but then shade it in to the right. Okay, let's try that one more time for the next inequality. I want to isolate the expression with the variable, the negative 2x. So I'm going to subtract 10 from both sides. I don't have to change the direction of the inequality. If I subtract 10 from 16, I get 6. But now, the next step, I've got that coefficient which is negative, negative 2. I'm going to divide both sides by negative 2. The minute I divide both sides by a negative, I'm going to have to change the direction of the inequality. So when I divide the left-hand side by negative 2, I'm just going to have my x on its own. When I divide 6 by negative 2, I'm going to get a negative number, negative 3. And here is the big important difference between equations and inequalities. I've got to change the direction of that inequality there. And so that's my solution. X is greater than or equal to negative 3. So I can diagram that. I'll put negative 3 right in the middle. A couple of hash marks on either side. So negative 2, negative 1, 0. Negative 4, negative 5, negative 6. It's usually a pretty good idea to test something other than the boundary value. I didn't do that for the previous example, so let's just go back up and do that, just to make sure that I'm going the right way. So let's try 5, for instance. 3 times 5 plus 5. Now that's 15 plus 5, which is 20. 20 is indeed greater than 17. In other words, it makes it a true statement, so it should be part of the solution. So let's go down here. We'll finish this number line here. Negative 3 is the boundary value, but this time the inequality is greater than or equal to. So I can fill in 3, that circle, because it is part of the solution. And then, since it's greater than, I'm going to the right. And let's test one of these values that's part of that solution. For instance, let's test 0. 0 is greater than negative 3. So what this diagram says is 0 should make the original inequality a true statement. Well, 10 minus 2 times 0 is just 10, and that is indeed less than or equal to 16. So that is part of the solution. So it's worthwhile testing not only the boundary value, but picking one number that's supposed to be part of the solution that's not the boundary value and seeing if it really makes it a true statement or not.